So for determining the mass of an unknown object, are
Mhm.
you going to give one of the three density, volume, or mass for us to figure that out? I'm sorry, are you going to give us either mass of volume, or is it going to be like in a word problem? And then like kind of how we had the example of the king's crown, and we had to
Mhm.
figure out, is that how that question's going to be framed for determining the density of an unknown object?
Well, I mean, if that's the only way to determine the density of an object, right, is to have the mass and the volume. So basically, there's three pieces of information. They're all related to each other. So if you have, oops, get that a little bigger. So if you have any two of those, you can solve for the third, right? So generally in the experiment, determine mass by just throwing it on a balance and seeing what the mass was, and then submerging it underwater and seeing what the change in volume was. That gave you the volume of the object, and then from that you determine the density. But I could just as easily say, if you had, let's say, a piece of lead that weighed, 44.41 grams, what is its volume? Something like that. I mean, just with the realization that there's only three things in this to know: density, volume, and mass. And you should be able to completely change those things around and either determine the density, the mass, or the volume, depending on what information you get. Is that the I'm not sure I understood the question
Yeah,
correctly.
that's fine. Yeah.
So you're wondering if like you might have to determine a mass from a density or a volume from a density, that sort of thing.
Sorry, you cut out there, Professor.
Oh, so you were wondering if you might have to determine the mass or a volume from a density?
I was just wondering if that sort of question is going to be kind of framed in a word problem, or just how it's going to be.
Could be either.
Okay.
Yeah, could be like a multiple choice. Here's the piece of aluminum or piece of lead. This is the mass. What is its volume? And then you have A, B, C, D, or E. And so remember, when just like on the lecture exam, you got to show your work. A lot of people forgot to do that. So there were some calculation questions in there with 4 or 5 answers, and they just circled one of the answers, and they only got half credit if they got it right, and 0 if they got it wrong. And for those who showed your work and got it wrong, you still got half credit. So it's definitely worth showing your work. Okay. Yeah. Any other questions about the first lab or any of the labs before we get going? I appreciate the questions. It helps to know that there's people alive out there. All right. So the first lab was basically would have been the same thing in the lab itself. This is the same basic experiment. One thing that people forgot to do in this particular lab was when they had their graduated cylinder with water in it, and then took their object, whatever it was, and then put it in the cylinder. If it was lighter than, if it was less dense than water, say it was like wood or styrofoam or something like that, it would float on the top. And they forgot you'd have to actually push it down under the water to get the volume to actually to be measured properly. And so that led to a problem with correctly getting the density, because what they demonstrated by doing that was, let's say they took like 30 milliliter size piece of styrofoam that has a density of 0.6 mgs per mil. And they put that in the water, and they noticed that it displaced 18 milliliters of water. And so they gave the volume as 18 milliliters. Well, I mean, what they proved there is that the object is going to displace the mass of the water that pushes back against its own mass. So the mass of this object would be 18 mils. It displaces 18 mils of water because water is 1 mg per mil. But that's not the volume of the object. The volume of the object is actually 30 mils, not 18. And so I got a lot of lab reports saying that like the density of the wood and the density of the styrofoam is all 1 mg per mil. That's the density of the water. That's why it displaced exactly the same mass of the object. So something to remember, because that might be a tricky question or something like that. Any questions about that? Most people remembered to push the object down, but not everybody did. And so if you got 1 mg per mil for something lighter than water, that's the reason. That's the reason why. But basically, the other thing to remember about this lab is the difference between accuracy and precision. That came up a lot in the remember that was like the very first question, I think, on the lecture exam. And almost everybody got it wrong because they didn't understand the difference between accuracy and precision. So there might be a similar question on the lab exam. So remember, the precision of a result shows basically how repeatable it is. Do you get the same answer every time you measure something within a very small error? Like if I measured 1 gram weight, whatever it is, like let's say I measured a nickel, the mass of a nickel. The mass of a nickel is around, I think it's around 3 grams. Let's say it's around 5. Let's say it's around 5. So I measure it and I get 5.001, 4.998, 5.002, 4.997. Measured it 4 times. Now, are these results accurate or precise?
Precise?
Gotta put my grams in there. Made a big mistake. Yes, they are precise. Are they accurate? Remember, the expected mass.
The series.
Expected mass is 5.00 grams. So you're correct. Those are precise
So they are
measurements, and they're accurate. They're both. If, on the other hand, I took my nickel, I went to a different balance this time, and I got 4.87 for 5.113, 4.787, and 5.211. What about these numbers? So you can check precise and accurate. Are they precise?
No, they're not precise.
No, not really. I mean, yeah, they're kind of all over the place, right? They're a little bit less, they're a little bit more. The errors in them are fairly large. So no, they're not precise. But are they accurate?
Yeah, kind of.
Kind of.
And they're close to 5, so
Well, yeah, I mean, how would you determine whether or not they're accurate?
by finding the, oh my God, sorry. By
Ooh, you
finding
all right?
the average.
Right, exactly. You gotta, is everything okay over there?
Yeah, my phone fell.
Yeah, because if you take the average, this kind of came out nice. The average is 4.997 grams, which is almost exactly right. So they're not precise, but they are accurate. And so you can have precision without accuracy. You can have precision with accuracy. You can have accuracy with or without precision. It all is a matter of remembering each individual measurement contributes to precision. The average of them tells you whether or not it's accurate. You have to take all of them together to determine they're accurate. Each individual measurement, if they're different from each other, are not precise, but they still might be accurate. And at the end, what a scientist is looking for is accuracy. You'd like to have precision too, but sometimes you can't have both. But if you could only have one thing, you'd rather have accuracy than precision. And so the other thing that comes with this particular lab, and pretty much every other lab, is significant figures. Oh my God, significant figures. How many people have had this written on their lab reports or their tests? Probably everyone, I would imagine. It's even more important in the lab exam and in your lab notebooks than pretty much anything else, because this is where you're reporting results of an experiment you do. You have to be able to express how precise your data is. And the precision is basically given with significant figures. Not so much the accuracy, but the precision is represented in the number of significant figures you can use. So how do you determine the number of significant figures? Who can give me an idea how to do that? Well, there's your problem right there. No one remembers how to do it. Someone get us started. How do you
Non-zero numbers.
non-zero numbers? Okay.
Non-zero digits are always significant.
The first count from the first non-zero numbers.
So non-zero numbers are significant. Okay. And what about a number like this? How many significant digits are in that one? This number here.
5.
5. Right. What
So-
about this? How many significant digits in 23,000?
2.
2. What if I put a
2.
period at the end?
Would that make it like an exact measurement?
Mm-hmm. That's the only reason for putting a decimal there. That's a number that a lot of you probably haven't seen before, because there's you don't really use it in mathematics, but we do use it in sciences where you do actual physical measurements. Because this with the period at the end represents that I was able to determine that there were precisely 23,000, not 23,001, not 23 or 22,999. That was the mass or the volume or something. That this number is precise, and the period at the end tells me that all the digits before it are significant, even if they're zeros. So the other thing to take in mind is when you have when you're doing when you're doing a calculation, like particularly in this example, this lab right here, when you're calculating the density of something, and that equals, that equals the mass divided by the volume. How are you going to determine how many significant digits to report the density? How do you do that?
The least significance.
What does that mean?
The least significance of mass or volume. Yeah.
So if I had 200 grams divided by 50.0 mils, what would the density be? Someone actually taking a calculator out?
4 grams per mil.
How do I express 4?
Just 4.
Just 4. Yeah, I can't put any more decimals in there because you are basically your precision is qualified at whatever your least precise measurement was. So my measurement here of 200 is not very precise because basically what that means, it's 200 plus or minus 99. So I know it's not 100 and I know it's not 300, but it's somewhere in between. That's really all you're saying when you have 200 without anything else. If I put a decimal at the end, then I could say 4.00 grams per mil because I would have 3 significant digits on the top and I'd have 3 significant digits on the bottom. So then my reported density should also have 3 significant digits. So that's really important because that came up all the time in lab reports, in exams, and in recitations. And most of the time, like 99% of the time, it was too many significant digits rather than too few. So be on the lookout for that because that is going to always be a part of chemistry, physics, anything where you're measuring something. Now, here's something different. How many significant digits in 12?
Infinite many.
That's right. Why is that?
It's a defined value instead of a measured value.
That's close to what we're looking for. Yeah, it's not a measured value. That's correct. What is it? Yeah, it's counted. Right. We're counting. And when you're counting something, that's an exact number. So, I have 5 fingers on my left hand. I have exactly 5. I don't have around 5. I have precisely 5. There's no other number so that's 5.0 to infinity. So if you're dividing something by a dozen, you don't worry about the number of significant digits in 12. Just assume there's an infinite number, and you're limited by the significant digits and whatever other number you're using. What about 2.54 centimeters equals 1 inch? How many significant digits in centimeters?
Still infinite?
Still infinite. That's tricky. It just happens to be that 1 inch is exactly 2.54 centimeters. It just kind of worked out that way. So if you're taking like cubic inches and turning them into cubic centimeters, yeah, you don't have to worry about the number of significant digits there either, because that's an infinite number of significant digits. So you can use as many for cubic centimeters as you like. So accuracy and precision are going to be super, super important with this lab and pretty much every other lab as well. So let's look at some of the questions. Probably looked at these hopefully already, because it's been a while since we did this lab. What's the difference between an extrinsic property and an intrinsic property? Intrinsic and extrinsic. Who? JCY. That's right. You want to tell everyone? Is your voice not working today? Oh yeah. Okay. I feel you. Yeah. Extrinsic depends on the amount of material. So. Mass is extrinsic, because it depends on how much stuff I have. If I have 100 grams of aluminum, I have 200 grams of aluminum, I have 300 grams of aluminum. It's all pure aluminum, but I have different amounts of it. So I can't say that mass of aluminum is something intrinsically essential about aluminum. No, you could have any amount of aluminum. Same with volume. I can have any volume of water. I can have a liter of water. I could have, a cubic meter of water. I could have, a trillion liters of water. It's all water. There's nothing essential about the amount of water. But what about the density? Is density an intrinsic or extrinsic value? Which one is it? It's one or the other. Does density depend on the amount of material you have? So quiet. Why is that, Francis? Why is it intrinsic? The same throughout what?
Throughout any amount.
Yeah, if you have a gram of aluminum, you have 10 grams of aluminum, you have 10 pounds of aluminum. If it's pure aluminum, the density is always going to be the same. You can actually use density, as we did in this lab, to identify certain things. You can tell the difference between, like for instance, copper and brass look fairly similar. Well, because there's copper in brass. Copper is brass plus tin. So you can tell if you put them side by side, sometimes it's kind of difficult to tell them apart because they look fairly similar. But the density of one is different from the density of the other, and so you can tell them apart because that's an intrinsic property of a material, is how dense it is. And then I don't know. I'm not really going to go through these calculations. They're fairly straightforward. If you want to do one together, we can. But did anybody have Oh, will all ratios be intrinsic? That's an interesting question. Generally, yes, if one depends on the other. The mass depends on the volume depends on the mass. So yes, those two are related. But there's other things that aren't, like, conductivity and mass, that sort of thing. They're not directly related. So that's a good question. I think there are some that would be two extrinsic values that when you divide them would be intrinsic, but I don't know if that's absolutely true for everything. That's a really good question, though.
If an intrinsic property is, it's intrinsic, but it changes by other factors, how do we say that?
What do you mean it changes by other factors?
So density is intrinsic, right?
Mm-hmm.
But it changes by temperature.
Mm-hmm. Right.
Do we still say that?
Yeah, it's still an intrinsic property, because the density of liquid water is always the same. The density of gas, water vapor at certain temperatures is always the same, depending on the volume, of course. And then the density of solid water is always the same. So depending on the temperature, but it's always the same. So like at minus 20, minus 40, it's always going to be the same. Yeah. Right. So when we measure this density, basically we're measuring it at standard temperature and pressure. If you remember what that was 25 degrees Celsius for solids and liquids at 1 atmosphere of pressure. Because the density of even liquid water changes with temperature. When it's warmer, it's slightly less dense, and when it's cooler, it's slightly more dense. All right. So do we want to move on to the next lab, or do you actually want to? Want to do one of the calculations?
I think moving on is fine.
Here you go. Next. Okay. So we did the paper chromatography lab next. We sort of learned what chromatography is. Anyone sort of give me a brief explanation of what chromatography means? What did you actually do when you did chromatography?
We separated ions.
These weren't ions. They don't necessarily have to be ions. It is a separation. That's the key. It is a separation. But it doesn't necessarily have to be ionic. In fact, we're sort of getting into, in class, we're sort of getting into why things separate. If it wasn't for charge, what's the other thing that we actually use to separate different molecules?
It was like the adhesion to itself or to paper. I forgot what that term.
Sort of adhesion. And what's that sort of related to? What is it about a molecule that makes it adhere to itself?
Polarity?
Polarity, exactly. Like water is one of the most adhesive liquid molecules there is, because it has such a big difference in its slightly negative side and its slightly positive side. So those things orient around, and water holds on to itself very tightly. And so you can basically explains why you can have like a redwood tree be like, 1,500 feet high, because you can pull a column of water that high, because all those water molecules are stuck to each other and stay together even though you're pulling it that high up in the air. And so with chromatography, you're separating things based on polarity. So what were the two phases that we use? What are the two things that we're basically using in chromatography to separate things?
It was a mobile phase and a stationary phase.
Right. So we have a stationary phase and a mobile phase. What does that mean? What is a stationary phase? What was the stationary phase in this lab?
Solid.
In this particular lab, though?
Paper.
Paper, right. In this particular lab, it was paper. So it's not always paper. It's a whole bunch of different things. But basically, you have two things. You have a solid support, and you have a liquid. And so basically what you're doing when you do chromatography is you have this complex mixture of things, and you're basically giving them a chance to interact with the solid support or with the liquid, or some ratio in between. And we use a fancy name called partition to sort of really mention this at the time. But basically, molecules will partition or separate themselves based on whether they have more affinity for the solid support or more affinity for the liquid. So if something has more affinity for the liquid, when we spot it on the solid support or on the paper, what happens to it? So if I take my paper and I spot my samples, I spot 1, 2, 3, 4. So if the green spot has more affinity for the liquid than for the paper, what happens to it as time goes on? As I let my experiment develop, what happens to it?
I think it was the one that has the affinity for the paper moves up the paper.
Okay. So if it was bound, let's say it's when we say something's bound, it means it's basically it has a high affinity for it. It's attracted to the paper. So if a molecule has more affinity for the paper, now remember, it's the liquid that's moving. The paper doesn't move anywhere. That's why it's stationary. We call it the stationary phase or the stationary support. It doesn't move, but the liquid is moving up. So here's the boundary of where the liquid is. Anyone remember what this is called? The boundary where the liquid?
Line.
What do we call it though? Sort of, remember, the solvent or the mobile phase moves up the paper, and then when it gets near the top, we pull it out. We mark it.
Oh, the solvent front?
The solvent front, that's right. We call that the solvent front. Now, if my green compound here, let's say the solvent is nonpolar. because it generally is. And the paper is polar. If the green molecule is nonpolar, is it going to stay where it is, or is it going to move up the paper? So I have a nonpolar solvent, or slightly less polar than water, anyway, like acetone or something. Acetone is still polar, it's just not as polar as water. So as acetone is moving up, the green spot is a relatively non-polar molecule. Is it going to move with the acetone, or is it going to stay where it is?
Barely move. Just stay. Maybe just stay.
So everybody's saying stay. Okay, so that one's going to stay. Now, what about the pink one? The pink one is polar. So this one is polar. So as my nonpolar solvent moves up, is it going to stay also, or is it going to move with the solvent?
Wait, did you say the green one was polar also?
No, I said it was nonpolar.
Then
So green is nonpolar, and the pink one is polar. Which one is going to stay, and which one's going to move?
the green one is stay. The pink one is moving.
Okay, anybody else? Ariana says move. Which one, Ariana, is going to move with the solvent? The pink one or the green one?
The pink one is going to move and the green one's going to stay.
Okay, so everyone seems to be agreed. So why is that? Why do you think if something is similar, if something is chemically similar to the solvent, why won't it move with the solvent? Like the green one is nonpolar, the solvent's relatively nonpolar. How come it doesn't move with the solvent?
Wait, the solvent is relatively nonpolar.
Yes.
Would
Okay,
it be
then the
because
opposite.
nothing
I
is
thought it
attracting
was,
to it?
Nothing is, what do you mean attracting to which? Attracting to what exactly?
Like the solvent doesn't have anything to pull, like the solvent doesn't have anything to pull the non-polar, like the green one.
Oh, but it does though. So if you compare the paper is polar and the solvent is more nonpolar than the paper, you're not going to really see anything that's completely polar and completely nonpolar. Things are, slightly one or slightly more of one, slightly more of the other. But the paper is more polar than the solvent. So if my green spot is more nonpolar than polar, it will partition or separate into the solvent. Like, as we'll find out, who's heard the expression like dissolves like? Probably heard that before. Anyone know what that means? Like dissolves like?
So polar solvent dissolves polar molecules.
Right, and nonpolar solvents dissolve nonpolar molecules. Because nonpolar molecules have more interactions with a nonpolar solvent, and a polar molecule has more interactions with a polar solvent. And the more interactions you can have with something, the more you stay bound to it. The more interactions you have with something, the more you stay with it. So if I have a polar molecule, like the pink one is polar, it will have more, excuse me, more interactions with the paper than it will have with the solvent. And so instead of dissolving into the solvent and moving with it, it's going to stay where it is because it has more interactions with the paper. On the other hand, the green one, the green molecule here has more interactions with the acetone. And so the more interactions it has with the acetone, the more stable it is in the acetone. And so it will move from the paper to the acetone. And as the acetone moves up the paper, the green spot will move up as well. So after a while, the green spot will move up and the pink spot will basically hardly move at all. It may move a little, but it won't move much. So it may move a little bit. Because like I said, no molecule is like completely nonpolar and completely polar. They're sort of, well, I mean, methane's pretty nonpolar. But there's sort of most molecules, most big molecules are a mixture of both. And so the more nonpolar you are, the more likely you are to go into the solvent. The more polar you are, the more likely you are to stick to the paper. Okay? So that's the way that's how the separation works. Whatever molecule has more interactions with, that's where it's going to be. If it's more interactions with the nonpolar one, because it is nonpolar, it'll move with the solvent. If it's more polar and has more interactions with the solid support or the paper, it's going to stay stuck to the paper. Okay, so that's important to remember because that's like one of the main things about chromatography that we needed to learn. So, and of course, we didn't really understand the difference between polar and nonpolar at the time. We're getting more of an understanding of that now. But this is really important to remember, sort of like dissolves like. So like if you take oil and water, you mix them together, everyone knows what happens, right? The oil, the water separate. But if you take oil and ether and you mix those two things together, they'll completely dissolve. Because ether is much more nonpolar than water is, and it will dissolve the oil, okay? So is that clear to everybody how that separation works? You move with what you're most like. So if you're most like the paper, you stay with the paper. If you're most like the solvent, you go into the solvent. Is that clear to everybody now? Yes, no? I'm checking the chat. All right, so what's the other thing? So that's like the role of the stationary and the mobile phase. The stationary will hold on to either the polar or the nonpolar molecules, depending on what the stationary phase is. You can have polar stationary phase like paper. You can have a nonpolar stationary phase like what's called reverse phase. Reverse phase is basically just like a long chain of carbons and hydrogens. So it's like really, really hydrophobic, very, very nonpolar. And then you'd move polar solvent across that. So things that are more polar would go into the solvent. Things that are more nonpolar stay stuck to the support. It depends. So the role of each one is to have a slightly different polarity than the other and allow the molecules to separate between one phase and the other phase. That's the whole point of chromatography, is that separation. So here's our spots. And then you already mentioned that how far the solvent goes is the solvent front. What is the retention factor. What does that mean? What's the RF? So I take out my chromatogram. That's what it's called. What you do, your final result is your chromatogram. I take it out of the solvent. I measure this distance. Whoops. I measure that distance. Let's say it's 43.5 millimeters. From the origin, this is the origin, because that's where I spotted everything, to the solvent front. How do I calculate RF? Distance of solute and solvent. So how do I measure the distance? Oh, okay, let's put my different spots here. So there's where I spotted them, and then there's where they went. So that one went there. We got one there. Got one here. And I've got one there. So how do I calculate the RFs for each one of these 1, 2, 3, 4 spots? You're close, Jovan. It's the other way around. Reversely. Yeah, you measure this distance between the spot and the origin. So that, what do we call that? What's our shorthand for that distance? What do we call it?
Displacement.
Or distance. But what do we actually, what's our shorthand for that? Anyone remember in the lab we did? Yeah, D spot, exactly. D spot, distance spot. So our retention factor is the distance of the spot over the distance of the solvent. So this is going to be the same all the way across if we did the experiment perfectly. If we did it in the lab, you would find that the solvent front is not a flat line. It'll look something like this. And so you have to measure the solvent front every place. It'll be slightly different depending on where on the paper. But for our purposes, it was the same each time. So is this an intrinsic or extrinsic property of the compounds in the spot? What do we think? Intrinsic or extrinsic property? What do we think? No one wants to talk today. Man, you're going to make me lose my voice. Why is it intrinsic? That's the more important question anyway. Why is it an intrinsic property? Someone better explain it to me. I'm not going anywhere. Right. Generally, yeah, the amount we spot shouldn't really affect how far that spot moves. I mean, if you spot too little, you're not going to see it, but it shouldn't really affect. So what we actually, so when you do this in real life, what you try and do is you spot as much as you can in the smallest area you can, so that when it moves, these things spread out as they move a little bit. They diffuse slightly, and so you want these spots to be as small as you can, so they'll be the intense. The colors will stay in a small boundary, and you can see them more easily. But yes, it shouldn't matter the amount. The distance it moves should be independent of how much you spot, and so it's an intrinsic factor. Every molecule should have a slightly different retention factor based on that particular stationary phase and that particularly mobile phase. If you change either one of those, you're going to get a different retention factor, but they should all then be different for everything else too. So that retention factor is specific for that compound, that stationary phase, and that mobile phase. Now, I'll ask a separate question. Is the distance traveled by the spot an intrinsic factor of the compound spotted? The distance, the D spot, is that an intrinsic factor? What do we think? Does the distance the spot move, is that an intrinsic property of the compounds in that spot? Man, how do I get everyone to wake up today? What do we think? Okay, Ariana, why do you think it's intrinsic? Why do you think the distance that the spot moves is an intrinsic property?
Because it's moving, but it's not actually changing anything.
I mean, it's not actually changing anything. It's an interesting way of putting it. So here's my spot, and I let it move up to, let's say it moves up to there. So you're saying that distance is an intrinsic property of the compound. So when you say it doesn't change anything, what do you mean?
Like it's not changing the amount of, like the matter isn't changing or the mass isn't changing.
Right. I mean, the distance, so in a sense, that is correct. The distance it moves is not dependent on the amount of material. Does that alone make it an intrinsic property?
Yes.
Okay. Do we have any other votes? Like your way of thinking?
So for the whatever the distance the a spot moves, the ratio would be the same.
What ratio?
The distance between the spot and the distance between the solvent.
So you're making the argument that the spot distance is intrinsic or extrinsic?
Intrinsic.
You think it's intrinsic too? Okay. Anybody else? We got 2 votes for intrinsic now. 1, 2. Do we have any votes the other way?
I have a question.
Okay. I love questions.
Would the amount of solvent matter of how much it moves? Like if we add more solvent, would it move further up?
It shouldn't. I mean, what you want to avoid, of course, is when you have your spot in there, you want the solvent to be below it. So when you put you would spot far enough up the paper that when you put it in, the spot wasn't below the solvent, because if the spot's below the solvent, it'll just dissolve in the solvent and not stay on the
It
paper.
depends on the time, but not on the amount.
Right, that is the issue. The distance the spot moves depends on the time. How long did you leave this in the solvent? If you leave it in for 30 minutes, the spot's only going to move to there. If you leave it in for 60 minutes, the spot's going to move to there. If you leave it for 90 minutes, the spot's going to move to there. So the distance the spot moves is dependent on the time. And if it's dependent on the time, it's not an intrinsic property. The ratio that the solvent front moves to the distance the spot moves, that's a constant. So if my solvent moves to there, my spot moves to here. If my solvent moves up to here, my spot also moves. But the ratio of those two will remain the same. So the retention factor, that is an intrinsic property. The distance isn't, because the distance is dependent on how long you let your experiment run. So the absolute distance is not an intrinsic property, but the ratio of the solvent moving to your spot moving, that is intrinsic. Yeah. So that one's a little tricky, because the way we've learned about intrinsic is that, well, if it doesn't matter how much we use, then it must be an intrinsic property. That's not always the case. If it depends on, how much time, or if it depends on the phase of the moon or whatever it is, it's not an intrinsic property. Like if it depends on, like the color of something, yeah, it's kind of an intrinsic property, but if you look at it in one light, look at it a different light, it looks like a different color. So it's dependent on the light. In this instance, it's dependent on the time. If you did it at the same time, you could say that it's the same distance. Just like if you look at something in the same light, you can say it's the same color. It's that sort of thing. All right. Is everyone clear on that? At least we got some discussion on it this time. All right. Is there any other questions about? We basically covered all this one, I think. Why does changing the solvent result in different patterns? Is the retention factor intrinsic or extrinsic property? Explain some of the chemical differences. I think we know what the chemical differences are now. Let's look at the third. Is there any other questions about experiment 2?
Yeah.
What?
Did you say paper is polar?
Mm-hmm.
And is it less polar than water, or?
It's a similar polarity to water.
Excuse me?
It's a similar polarity to water. It's not as polar as water, but it's similar.
So paper wouldn't be a good stationary phase for solvent as water?
No, not really, because both things are basically everything would just stay where it was.
Okay.
Yeah.
Professor,
Yeah.
I just want to make sure, is acetone polar?
It is polar. It's not as polar as the paper. So acetone looks like this. This is what acetone actually looks like. This is what the acetone molecule. So you can see with acetone, basically has a non-polar side, where it's just all carbons and hydrogens, where there's not very much difference in electronegativity, and it has a polar side where we have an oxygen with lone pairs. So there's more electron density at the top, and there's less on the bottom. So we have a dipole going like this. But what these molecules can do is like orient themselves. So things that are nonpolar will sort of interact with that side, and things that are polar will interact with this side. That's why it's a good solvent. It's a good nail. That's why it's used as a nail polish remover, because it can dissolve both nonpolar and polar things. It can do both. Whereas water is basically, it's all polar. There's really no place for a nonpolar molecule to interact with water, so it doesn't. So everything is relative. So yes, there is a dipole in acetone, but it's not nearly as big as the one that's in water. And it has two sides. And you'll see that, especially when you take biochemistry, and you're all going to take biochemistry, you'll see that biological molecules have various sides, different sides to them. And proteins basically have a hydrophobic interior where it interacts with itself, and a hydrophilic or polar exterior where it interacts with water. That's how
But
it can
carbon
keep an
monoxide is
inside and an
polar, right?
outside.
Carbon monoxide is polar, right?
Yes, but
So
not.
why wouldn't it dissolve in water?
I think well, some of it does dissolve in water. It's not. It can dissolve in water, not completely. I mean, gases have a hard time dissolving in water because they move so much.
Okay.
Yeah. All right. Yeah. So great question. Any other questions about experiment dose?
The error analysis questions had me a little bit confused because they felt so similar, and I thought they would require the same answer, but they're
Okay.
all, I know that they're different, but they're just, I don't know, the whole
look
thing
at
was
it.
just confusing to me.
Yeah, one of them was really kind of confused. The main thing because the third one is kind of just, the third one we could ignore. That was a weird question. But the first one was basically, so I've got my chromatogram, and so I put my spots in it. And basically what I did was I allowed the solvent to go all the way to the top and just basically just keep going. So what the solvent would do is it would move to the top, get to the top of the paper, and then basically go into the air, and then more solvent would come up after it and then get to the top and then evaporate and then just keep going and evaporating and keep going. So what's going to happen to these spots if we just let the solvent basically keep moving? Because you have to remember, the solvent's not going to stop moving. It's like, yeah, like acetone in particular, when the acetone gets to the top, it's just going to turn into gas and evaporate and then be replaced by more acetone coming up from the liquid. So these spots are just going to keep on moving. They're not going to stop just because it looks like the solvent has stopped. It hasn't stopped. So how does that affect the retention factor? If I let this go for like an hour after the solvent reaches the top, is my retention factor going to be more or less than if I had stopped it earlier? That's basically the first question. It asks you if it's an overestimate or an underestimate, if you let it run longer.
So would it be more because you kind of just let it keep going and that would bring the distance higher?
Exactly. Yeah, the spots are just going to keep moving. And if you leave it long enough, the spots will just all sort of just be on the top. The spots aren't going to evaporate because those molecules are big. They're not going anywhere. But the solvent, those molecules are small. They're going to evaporate. And so basically, the D solvent stays the same because it's just the top of the paper. But your D spots keep going up and up and up until eventually they're all the same. So when all the spots are at the top of the paper, then the D solvent and the D spot will be the same. That'll equal 1. They'll all equal 1 eventually. So that's why you have to stop it before the solvent front gets to the top. Now the second question was, what if instead of letting it go too long, we stopped it well before the solvent got to the top? So we put our spots in the paper and we stopped it when the solvent got there, rather than letting the solvent get to the top. Now, what'll happen to the D spots, the D solvent, and the RF when I only let the solvent go like halfway up? What happens to the distance of the solvent first? Is it going to be more or less?
It's gonna be less.
Yeah, it's going to be less. What about the distance of the spot? Is that going to be more or less?
That's also gonna be less.
Yep, also going to be less. What about the ratio of the two? The RF?
Not affected.
Not affected. That's going to be exactly the same. Because if my RF is 0.5, if my D solvent is 10 millimeters, my D spot is going to be 5. If I let it run longer, so that my D solvent is 25 millimeters, well, now my D spot is going to be half of that again. It's going to be 12.5. No matter how long I let that solvent go, unless I let it run off the top, my D spot will be exactly half of that. So the RF is constant. It won't change. And so if I don't let it run as far as usual, it shouldn't affect my result. My RF, my retention factors, should theoretically be the same. I mean, in real life, it's kind of hard. If they don't move much, it makes it difficult to measure them. But realistically, the RF should stay the same.
So it only matters if you just let it run more than what it should.
Right. If you let the solvent run all the way to the top, that's a problem because now you don't know what the distance of the solvent is. The only thing you can measure is the top of the paper. But really, it's farther than that because the solvent just keeps going. It just keeps moving. So the distance the solvent has actually moved is actually more than this distance. It's moved more than that because it's moved to the top and it's kept going. So the solvent just keeps moving and moving and moving. And so you underestimate the distance of the solvent. And when you underestimate the distance of the solvent, you then overestimate the ratio. Yeah, so you always want to stop it before it gets to the top.
Oh, okay, that makes more sense.
Oh, good. Something made sense today. I'll have to make a note of that. Thanks for asking. Man, I'm getting tired of hearing myself talk. Man. All right, so number 3, gravimetric analysis of arsenic. What does gravimetric mean? There's the first question. What does that mean? Gravimetric. Sounds like gravel or something. Where does gravity come from? Is it a gravel analysis?
Measurement based on weight.
Measurement based on weight. Okay, so where does the grava come in? But where does that come from?
Grava means precipitation.
Yeah, it means gravity. Yeah. Something involved with gravity. So when we do a reaction, involving gravimetric analysis, it means something is falling because it's involving gravity. So we're doing a precipitation reaction. So we're forming something that is no longer soluble in whatever solvent it is we're in. And we were working in an aqueous environment. And aqueous means what? What solvent does that mean? If something's aqueous, what is that? Where is it? If I have an aqueous solution of salt, it means I have salt. Right, Ferris. It means it's dissolved in water. Agua. Agua if you're Spanish. Aqua if you are French. So, yes, that means that it's dissolved in water. So, if we're making something, if we're taking ions, in this instance, we're taking ions. You remember arsenate was this. That was the ion we were looking to precipitate. So it's in solution. So it's dissolved in the water, meaning it's not a solid. It is an ion in the water. And what did we add to get it to precipitate? Anyone remember what we added?
Silver.
Silver. Yeah, we added a silver solution, right? We didn't just take a solid piece of silver and drop it in, because that wouldn't have done anything. Why wouldn't that have done anything? If I took like a solid piece of silver and dropped it in a solution, how come that wouldn't have precipitated my arsenate ion?
Silver doesn't react with water.
Not just that.
And if you have silver in precipitate, we don't know which one is silver, which one is the silver arsenate.
No, I'm sort of look. What's the reaction that takes place that causes this to precipitate?
Silver ion with arsenate to precipitate silver arsenate.
That's the key. It isn't silver that interacts with arsenate to precipitate. It's silver ion. That's the key to the whole thing. It's an ionic reaction. You have ions interacting with other ions, forming an ionic compound that is no longer soluble. Ag3ASO4 is not a soluble solid in water. And so it forms a solid, precipitates out. And then we measure the mass of this, right? So how do we figure out how much arsenic was present by measuring the mass of silver arsenate? There's an awful lot going on there. How do you go from silver arsenate, Ag3ASO4, to just measuring the mass of arsenic?
The mass percentage of the arsenic in silver arsenate is constant.
And so that was one of the ways we wanted the data to be presented in this particular lab. You remember, was the mass percent. And one thing that people forgot was that the samples you were given, there was like I think 3 different samples. One was a solution of arsenate, I think sodium arsenate, and the 2 others were unknown samples that were extracts from soil. And what most of you forgot was that the soil samples were from 1 kilogram of soil. And so that had to be the denominator in determining the mass percent. So basically what we were looking for was grams of arsenic over grams of soil. Even though it was a solution, basically what happens, you take the soil, you mix it with water. You shake it up, and then you dissolve all the arsenic you can, all the arsenate you can, into the water, and then filter it, get rid of the soil, and then use that to precipitate the arsenate. But the actual amount of arsenic that we started with was from 2,000 or 1,000 grams. It's either 1 kilogram or 2 kilograms. So you should have divided by 1,000 grams of soil. Some of you did that, most of you didn't. I just sort of made a little note of it. So this is just basically just straight up stoichiometry. Most people did this fairly well. The only problems were, the usual things: significant digits and remembering that the precipitated sample was this rather than this. So people took this as what they should as the mass, what they should calculate. Actually, the overall mass has silver and oxygen in it rather than just the oxygen. So these were the basic questions with this one. So most people got the idea that why was it necessary to know the density of the arsenic solutions to calculate the mass percentage? Why was that important? How come we couldn't have just used the density of water and figured out and just use that? Why do we have to have a density? Isn't water good enough?
Because they have different densities.
Yeah, water with something dissolved in it doesn't have the density of water anymore. So, but why is it important to know the density anyway?
And in volumes.
Let someone answer, Raymond. We know you know. Why do we need to know the density of the arsenic solution? What are we trying to calculate here? When you calculate a mass percentage, what does that mean? Yeah, you have to know the density of the arsenic solution to calculate the mass percent. Why? Why? How come? Man, it's going to take a long time if we're just going to wait for you guys to answer. Most of you answered this question, so just what is the density of the arsenic solution? What information does that give you that allows you to calculate the mass percentage?
Is it the mass of the solution?
Right, you need to know, why do you need to know the mass of the solution?
So that we can find the mass percentage?
So when I do mass percentage, what do I put on the top and what do I put on the bottom?
The mass percentage of arsenic and divided by the total
in a
mass.
solution. Yeah, if I want to know the mass percent of arsenic in a solution, I put the mass of what on the top? What goes in the numerator there? Yeah, I want the mass percent of arsenic in a solution. So the numerator, that expression, I put the mass of what? The mass of the precipitate? So Giovanna, put the mass of the precipitate on the top. And mass of the solution on the bottom. That is incorrect. I like how you were forceful though. What do I put on the top? I don't put the whole precipitate. Why don't I put the whole precipitate mass? So my precipitate is silver arsenate. How come I don't put the mass of that whole thing in the numerator? Right, you don't want the silver. You actually don't want the arsenate either. What you're looking for is just the arsenic. So you take the mass of the precipitate, Ag3ASO4, and then you figure out how much of that is just the arsenic. And that mass is what you're going to put in on the top. And then on the bottom is the mass of the whole solution. I think the density was 1.05 grams per ml times whatever the amount you used to do the precipitation. If you use 50 mils, you'd use 50. If you used 100, whatever it was. But yeah, you don't put the mass of the whole precipitate, just the mass of the arsenic. If you want the mass percent of arsenate, then you use the arsenate. But if you just want arsenic, just have the arsenic there. So the last question, the second one, people came up with a lot of different things. I was just looking for you to just look up some other stuff. There's a whole bunch of other things to detect specific elements. A lot of you recommended drying the solution and looking at what solid was left over. Well, that'll work if it's completely pure substance that's in there. But generally, there probably isn't. There's probably going to be a whole bunch of things. And so you'll be drying out everything, salt and solids and sugar and whatever dissolved crud that may have fallen into it. So that's not really going to work. You need something more specific. So at the third one, I'm kind of curious about. So I want to precipitate arsenate, ion. Why is it necessary to choose? Now I'm going to put a cation in there, right? I'm going to put some sort of metal cation in there to interact with the arsenate and precipitate it. Why is it important that I choose this metal carefully? That metal ion. Why is it important that I choose the metal ion carefully?
To make sure it doesn't react with anything else or precipitate with anything else.
Yeah, exactly. I mean, it's really tricky to do something like this and make sure that the only thing you're precipitating is arsenate. So you try, but basically what you try and do is find a metal ion that won't precipitate a whole lot of other things. Silver is kind of tricky because silver chloride isn't particularly soluble either. And so silver will precipitate other things. But what you try and do is find something that will generally precipitate as few other things as possible. It's basically impossible to find something that won't precipitate anything else. But also, you don't want a metal that's going to precipitate every other ion present in the solution. You want to be as selective as possible. So yeah, that's why that's necessary. All right, let's do. Oh yeah, and then so the air analysis questions. Yeah, most people got the first one. Yeah, if you don't add enough silver nitrate, you're going to underestimate the amount of arsenic. That makes sense. The metal sulfate hydrate. I don't know how many people actually read the, oops, go back. How many read the lab manual? What's going on here? There we go. Yeah. Why? Here we go. I don't know how many people read the lab manual, but this is an experiment that we normally do in 210. And what hydrate, a metal sulfate hydrate is, it's basically a metal, and then it has this that's linked with a sulfate. So it has an ionic bond with sulfate. Well, sulfate has so many charges on it, and it's very, very polar, that it attracts water. And it attracts water so tightly that it's actually physically associated with it. So that when you're like digging this out of the mine or whatever, you have a crystal of this stuff, there's actually water inside the solid. That's how tightly it's associated. But it's not covalently linked to it. It's just very, very tightly associated, much like the chromatography example we talked about. The metal sulfate is super, super polar, and so it attracts water very, very tightly. In fact, so tightly that the water stays part of the solid. But when we heat it, the water is driven away because it's not covalently linked. And if you just heat it up, the water turns to vapor and disappears. So your question was, if you have this sample in a test tube and the test tube already has water in it. So let me get a whiteboard. Here we go. So if I have my test tube here, here's my sample of the hydrate. So that's M sulfate hydrate. If I already have water on the sides of the tube, before I start heating it, am I going to underestimate the amount of water or overestimate? Now remember, I'm trying to figure out how much water is present in this solid at the bottom. So what's going to happen? Am I going to overestimate the amount of water? Am I going to underestimate the amount of water?
You're going to overestimate?
Why is that?
Because when you first weighed the test tube, let's just say it was 10 grams.
Mm-hmm.
And then after you weigh the test tube, you'll think it'll be 8 grams, but realistically there was only 1.5 grams of liquid. That extra 0.5 grams will come from the water that was built up on the side that you didn't dry off.
Yeah, exactly. That difference in mass, that delta mass, is going to be higher than it should be because it's also looking at the mass of water that's on the side. So I'm going to have, it's going to look like I've lost more water than I actually have. So my delta mass will be overestimated. And it's the delta mass, it's the change in mass that tells me how much water is present in this molecule. So that will be an overestimate. Now this second one was a little trickier. What happens if I don't have water on the side? Oh. All right, here's my tube. So there's my tube. I don't have water on the side this time. But what happens is some of this solid, actually, but I'm heating it, and this will happen. If I heat it too quickly, I get steam forming underneath my solid. And then when the steam, basically bubbles up, it ejects some of the solid sample out. So when that happens, am I going to overestimate or underestimate the amount of water present in my sample? So I didn't have water. I took care. So when you actually do this experiment, you actually heat the the test tube. You heat it and you heat it and heat it until it stays the same mass, because now you've got all the water out of it. Then you put your sample in. So now I put my sample in, but I heated it too fast, and a little bit of the solid came out. Is that going to underestimate the amount of water I have in my sample, or overestimate the amount of water in my sample?
It'll be a overestimate.
That's going to be an overestimate too, right? So explain why that is.
You'll have the same volume of water, but you'll think that sorry, just one sec. So your test tube will weigh less, but you'll still have the same volume of water. So that'll give you an overestimate.
Yeah, basically I mean, you're right. I mean, basically what it means is that this loss in mass will assume to be will assume to be just water. And so if you lose some of the solid, that's going to assume to be water. And it isn't just water, it's the solid too. So you're overestimating the change in mass. So your delta mass is overestimated. And if your delta mass is overestimated, the amount of water is going to be overestimated as well. So both of those situations cause an overestimation in the amount of water present. Does that make sense to everybody? Some people said underestimate because, you could, because the water left with the sample. But the key to the whole thing is you won't be able to put the sample, you can't put back in now because it's contaminated, or you didn't even see it at all. You didn't see that you lost some sample. So whatever mass is missing, when you measure the mass after heating, you're going to assume that change is water, and it's going to be more than it should. And if it's more than it should, that's an overestimation. Okay. All right. Let's go back. All right. Let's go a little while longer. And then any other questions I can answer tomorrow. So stoichiometric coefficients. This one was pretty straightforward, I hope. So basically, we just started with four molecules. That's all the information we had. All we knew was that they interacted with each other and they formed some sort of compound. So we had A and B and C and D, and that we know that they interact and then recombine to form one of the other compounds. So A and B make C, or C and D make B, or whatever. And so we started by putting 25 mils of each one, or 10 mils of each one, the same volume of each one. And they were all 1 molar in concentration. So what would be the concentration of each one after we added them all together? If I have 25 mils of each one in my beaker, what's the concentration of A, B, C, and D? So each one was 1 molar when we started. I mixed the 4 of them together in equal volumes. What's my concentration of all 4 now?
Is it 0.25?
Yeah, 0.25 what? Moles?
Molarity.
Molar. Just like your
Oh,
molar.
molar. Yeah.
Yeah, just like the tooth. Right, molar. So how do we know when something's a reactant and something's a product? So this is what we would call the concentration initial. And then something would happen and we would get the concentration final. So what are we looking for so we can tell the difference between a reactant and a product? How do we know when something's a reactant or a product? Oh, that's capital M, Raymond, not small m. That's molal, that's a different thing. A reactant decreases. Decreases in what, Ariana? Decreases in concentration. Right, so if something's been consumed, then we will assume it's a reactant because our reactants are going to go down in concentration because they're getting gobbled up. So if A goes from 0.5 molar down to 1.25 molar, that is a reactant. Now, what about a product? What happens to a product? If one of these things is a product, what happens to its concentration?
It increases.
It increases above what?
0.25.
Right, exactly. So if my concentration is now greater than 0.25, well, it's got to be a product because now there's more of it present than there was before. So if something went less than 0.25, that's going to be a reactant. If something goes above 0.25, it's going to be a product. And then trying to figure out the ratios of one to another, basically what we're looking for is what was the increase in concentration of my products related to the decrease in concentration of my reactants. Now, if my reactants decreased twice as much as my products did, let's say afterwards I have 0, oh, not millimolar, sorry about that. I have 0 molar A and 0.125 molar B and 0.50 molar C. D hasn't changed. What's the reaction that took place here? So this is my concentration of A, it's now nothing. That's my concentration of B. This is my concentration of C, and this is my concentration of D. What's the reaction that took place? Now remember, I want to look at what's the ratio of things going down to things going up. How would we figure that out? Figure out what's the change in concentration of A and B and C. How much did A go down? How much did B go down? How much did C go up? So what's my change in A? What's my change in concentration of A? if the initial was 0.25 molar, and now it's 0, what's my change in A? Right. Right. Ferris points out that my change in A is, let me make some more room here. All right. Change color. So, whoops. So my change in A is minus 0.25 molar. What's my change in B? So if my change in A is minus 0.25 molar, what's my change in B? Here's the new concentration of B. Right, Nick. So my change in B is minus 0.125 molar. What is my change in C? Right. Right, man, it is plus 0.25 molar. And my change in D is 0. So D is not involved. Well, we'll get to that in a minute. So A changed twice as much as B, and C changed twice as much as B as well. What's my overall reaction? Nope. Ferris, you're close. What's another way of putting that, Nang? That's right, but what's another way of putting, how would we actually express that? Because remember, we need whole numbers. So Nang suggested, and she's right, A plus 1/2 B makes C. That is correct. That's right. I mean, but if we want to look at whole numbers, right, we want to multiply everything by 2. So it would be 2A plus B equals 2C. That would be our reaction. So everyone sees how that works. Hopefully, I mean, pretty much everybody got this. The only problems, some people sort of forgot that like the last thing they were supposed to do was to have only reactants at the beginning. So in the exactly right ratios, so we would only have products at the end. In this particular instance, with 2A plus B makes 2C, what would we put in the beaker to make sure that we only had product at the end? So here's my reaction. 2A plus B makes 2C. So I want to put two things in the beaker that at the end, those two things will be completely gone and the only thing I will have left is product. What would I put in there? You can just get volumes of A and B. Remember that the concentrations are the same. So what would be the volumes of A and B you would need?
20 milliliters of A and 10 milliliters of B.
Exactly. And it could be any volume, as long as you had twice as much A as you had B. You could have 40 of A and 20 of B, or 100 of A and 50 of B, as long as you had twice as much A, because it takes twice as much A as B to make C. That's exactly right. So at the end, you'd only have C being present. That's correct. So the only other thing that was kind of an issue with this particular lab was figuring out what a catalyst is. Some people sort of got it what a catalyst is, other people not quite. What does a catalyst do? You can tell me what a catalyst does. It's sort of, it's sort of right there, right? But what some people didn't understand was they put if the temperature didn't go up, it couldn't be a catalyst. That's not how a catalyst necessarily works. So a catalyst does not have to increase. I mean, that's how a catalyst works basically. Is it doesn't have to increase the temperature in order for the reaction to go faster. So changing the pH or changing the temperature, that's not necessarily how a catalyst works. It just speeds up the reaction. The reaction just happens faster. That's it. And so how would we prove that one of these things is not a catalyst? Let's say in that last reaction we did. So we had 2A plus B makes 2C. How would you prove that D is not a catalyst? That's right, Ryan. Lowers activation energy through a variety of means, like an enzyme would, right? How do we prove that D isn't a catalyst? Because when I did the reaction the first time, reaction took place in the presence of D. How do we make sure that's not a catalyst? So nothing changes when you add D. What do you mean by nothing? Like my hair color doesn't change? Does not react faster. Right. So basically, the reaction can still occur if I take D away. So let's say in the first reaction we did, we had A, B, C, and D all present at the same time. So D could have been a catalyst. But if I take D out and just have A and B together, and they still make C, and they still make C at the same rate, that's the important thing. If it takes overnight for C to happen, for the formation of C to happen, but in the presence of D, it happens in 2 minutes, well, then D is a catalyst. So the reaction can still take place, but it happens much, much, much faster. So yeah, that's how you would do it. You take it out, and if it occurred at the same rate, then it's not a catalyst. And probably the last thing was that particular lab gave you the concentration of protons and hydroxide ion. So how would you know whether an additional product or an additional reactant, and this happens all the time, there's lots and lots of acid and base catalyzed reactions that occur. How do we know that that's not a catalyst, but an actual product or a reactant? How do we know that neither one is a product or a reactant? It could have been a catalyst. That basically, that's really hard to figure out, since they're always present at low concentration. But how can we tell if it's a product or a reactant? What would happen if hydroxide ion was a product of our reaction? How would we know? Right, Nan, we'd measure the pH. So what would happen to the pH if hydroxide ion was a product?
pH will go down.
So down, remember pH goes down when it's more acidic. So when the concentration of H plus goes up, the pH goes down. So if we made more hydroxide ion, would the pH go up or down? Would it
Up.
it would go up, right? The pH would actually increase, because if we have more hydroxide ion, when that goes up, it reacts with H plus, makes water, reduces the concentration of H plus, and so our pH increases.
Excuse me.
Yes.
This only applies for all neutral reactants, right?
I don't. What neutral reactants? What do you mean?
So if there are some acidic or basic reactants, but they don't involve in reaction, and so if there's dilution or concentrate dilution in there, that pH also changes.
If we just dilute, yes. Yeah, the dilution would affect the pH.
So if we add two solutions together, the solution would dilute, right?
Yes, but here we have water. We don't have an acid or a base. We just have water. So we're not adding an acid or a base. So if we add water to water, we're not really changing the pH.
Okay.
Okay?
Mm-hmm.
All right. So we've gone through 4. Does anyone have any questions on the last 2 before we go? Because we've been here almost 2 hours. Is there anything on the last 2 labs you want to discuss before we call it a day? So 5 is the molar mass of an unknown weak acid, and 6 was the electron configurations and atomic size. So any questions you want to review on either 5 or 6?
So what I meant is if A, B, C, D, one of them is acidic, and you add them together, the pH also changes, right?
Yeah, but you could just dilute it by 4 times and see if the change in pH was different. You'd run a control for that. Yeah, you'd see the difference between the dilution and the reaction. So any questions about experiments 5 and 6? If not, I will also be having office hours tomorrow at 11. So if you want to ask questions about them then, we can do that. Or, no, Yeah, we have a definite answer. So everyone's cool on. So I would make sure you know what standardization means. Titration is important. Titration is going to be super, super important. Know the difference between monoprotic, diprotic, triprotic acid. That's going to be important. So because a lot of people, when they did the recitation on this, didn't write out an actual chemical reaction. They didn't have a balanced chemical reaction. And so if we had a triprotic acid, that would be H3A. And so it would take 3 moles of hydroxide in order to get all 3 of those protons removed. So you need to write a balanced chemical reaction. If it's a diprotic acid, it would be H2A, and you would need 2 moles of hydroxide to titrate it. So make sure that you don't fall into that trap, like a lot of people did. We assumed that we had a monoprotic acid for this lab, but very well you'd have a diprotic or a triprotic acid as well. In the lab we do for reals, I think we use mostly diprotic acids, and so you need to take that into consideration. Okay. So again, any questions on this or 6 or anything else? I'll be available tomorrow at 11. So just drop by for office hours, okay? All right.
Professor.
Oh, yes. Go ahead.
For our exam, is it just going to be like all of the labs combined with like different aspects of all the labs, or is it just going to be like a whole new big lab?
A whole new big. What do you mean a whole new big lab? I mean, I'll ask you like questions about each one, and there may be like a tweak, like I'm saying here, like maybe you're given a diprotic weak acid rather than a monoprotic weak acid. How would you handle that? What if it was an unknown weak base? What would you do then? That sort of thing. So that I know you understand what it is we're doing in the lab. But I wouldn't like invent a whole lab out of like whole cloth and ask you to ask questions about that. It'd be very, very, very much related.
Okay, that makes sense. Thank you.
Yeah, sorry, I didn't really quite. Yeah, I mean not mean, but I mean that's the bonus question will be mean. That's always mean, but yeah, the regular questions won't be. So there will be a bonus question worth 5. It'll be, the test is out of 50, so it's actually out of 55, but I don't count the 5. So it is possible to get a score of 55 out of 50 if you do a really good job. So that'll boost some scores. Any other questions before we go? I have dogs dying to go for a walk. All right. So if I don't see you tomorrow, I'll see you on Thursday during the test. I will be available during the whole time. You can send me, messages, emails on Canvas with questions like, what are you doing? Why are you doing this to us? I'll answer them as quick as I can. Okay. All right. Thank you too, Niet. I'll see you later.